Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 just asks, what is mass percent? Okay, so let's write a general equation for mass percent. So mass percentage is equal to the mass of our component divided by the total mass multiplied by 100. So the mass percent can tell us a lot of different things, or it can be helpful in figuring out the composition of either a mixture or even like finding out like if we were given the total molar mass of a substance, then we can, and we know the sum of the masses of the other elements that are involved, we can probably find out the missing element and so on and so forth. So that's why I kind of kept it more general, because it can be used for a lot of different things, or even if we had a mixture of product and we knew the mass of one of the products that were involved, but we didn't know the mass of the other, but we knew the total mass, then that's another way we can find out mass percent. So let's see what the junior tutor said too. The mass percent shows the percent of the ratio of the mass of the solute and the mass of solution. Mathematically, it can be expressed as mass of solute divided by mass of solution times 100. So this is also another example where you can use mass percent in terms of solutions. They also said that since in a solution there are a solute and solvent, the equation above can also be expressed as the following. The unit can be in grams or kilograms, and it can be noted that mass percent is unitless, is a unitless value presented in a percentage. If the mass of the solute and solvent, I'm assuming, are not stated, it can be multiplied by the number of moles and the molar mass of the given compound. Okay, so this solution is correct. Mass percent can be calculated for solutions. I'm just going to add a more general formula. Okay, so I just added a general formula. just since we can use this equation for more applications. Okay, so question number 2. 2a, how many valence electrons are assigned to oxygen when determining the formal charge in the ionic compound sodium methoxide? And part B, which substituent has higher priority? Okay, so this is a 2-part question. Okay, so this is sodium methoxide. And it might be more helpful to show how how to answer this question just by drawing out its Lewis structure first. So to draw out the Lewis structure of sodium methoxide, we need to calculate the total number of valence electrons. So sodium has 1, oxygen has 6, carbon has 4, and hydrogen also has 1. But since we have 3 hydrogen atoms, we multiply this by 3. Okay, so now we can kind of draw a general skeletal structure. So carbon has the 3 single bonds to the hydrogens, and the sodium and the oxygen are bonded together through an ionic bond. And if we count out how many electrons we've drawn so far, where each bond contains 2 bonding electrons, then you can see that we only have 10 out of the 14 total valence electrons in this structure. So for the remaining 4, we'll put them on our oxygen. Okay, so now let's calculate the formal charge of the oxygen. So the equation for formal charge is the number of valence electrons, which is what the question was asking for, minus the number of non-bonding electrons, minus the number of bonding electrons, divided by 2. Okay, so for oxygen, oxygen has 6 valence electrons, and there are 4 non-bonding electrons, and since there are 2 bonds to oxygen, we have 4 bonding electrons divided by 2. So the formal charge for the oxygen is equal to 0. So this is the formal charge when it was ionic bonding with the sodium. But a more accurate depiction would be to separate the ions for now. And let's calculate the formal charge when oxygen is not bonded with the nitrogen, or sodium, sorry. So again, it would have 6 valence electrons, 4 non-bonding electrons, but this time there's only 1 bond, so we have 2 bonding electrons divided by 2. So 6 minus 4 minus 1 is 1. And let's do the same thing for the sodium. We can show that the sodium will donate or give its electron to the oxygen, like so. And after it does that, then we can calculate the formal charge after sodium gives one of its electrons. Okay, so now this changes things a bit. Okay, so now the number of non-bonding electrons is 6. And now there are 2 bonds, or 1 bond and 2 bonding electrons on the oxygen. And this is how we would get -1 as its formal charge in the ionic bond. Okay, so now if we look at the sodium, sodium has 1 valence electron, and there are no lone pairs on the sodium. So we just write 0. And it doesn't, when the bond isn't formed, and it just gave one of its electrons, then we also write 0 bonding electrons divided by 2. And this is how sodium gets its positive charge. Okay, so, and now they can form an ionic bond because they are oppositely charged. Okay, so now let's look at part B, and probably just fit it here. Which substituent in this has the highest priority? So we have a compound that contains mainly carbons and hydrogens, and they point at the different carbons. But since there's a bromine on substituent 1, this gives it a higher priority. Okay, so in this case, bromine, since it is a substituent that is not carbon, or it has, yeah, it's a substituent that is not carbon or hydrogen, this is why it is the highest priority. If there was an alcohol group on this compound, then the alcohol would have a higher priority than the bromine. But since the bromine's the only one here, then it has the highest priority. Okay, so the junior tutor said there are 6 valence electrons for oxygen when determining formal charge. And for B, to determine the substituent with the highest priority, examine the electrons directly attached to the stereocenter of the compound. A substituent with a higher atomic number will have a higher priority than the substituent with a lower atomic number. If the chains are similar, proceed down the chain until there is a point of difference. In this case, substituent 1 has a bromine atom present. It has a higher atomic number than the carbon atoms present on other substituents, Therefore, substituent 1 has the highest priority. Okay, so the solution is correct. Okay, so question number 3 asks, what is the molar mass of ammonium chloride? Okay, so to find the molar mass of ammonium chloride, we would need the individual molar masses of each of these atoms involved. And these molar masses can just be found on the periodic table. So for this compound in particular, we have a nitrogen atom, so we need to add the molar mass of the nitrogen atom plus 4 times the molar mass of hydrogen, since there are 4 hydrogens in this compound. And lastly, we would add the molar mass of chlorine. Okay, so if we look at a periodic table, we'll see that nitrogen has a molar mass of around 14.01 grams per mole, and hydrogen has a molar mass of 1.01 grams per mole, and lastly, chlorine has a molar mass of 35.45 grams per mole. Okay, so if we add all these values up, we get a total molar mass of 53.5 grams per mole for ammonium chloride. Okay, so the junior tutor said that the molar mass of a compound calculated by getting the sum of the molar masses of the constituent atoms. Ammonium chloride contains 1 nitrogen, 4 hydrogens, and 1 chlorine atom. The molar mass of each constituent atom is given below. Multiply the molar mass of each element by the number of atoms of that element present in the compound. Then get the sum to obtain the molar mass of the compound. And they also got 53.5 grams per mole. So the solution is correct. Okay, so question number 4. It says that oxalic acid which its molar mass is 126.07 grams per mole, is often used as a primary standard for the standardization of a sodium hydroxide solution. If 0.147 grams of oxalic acid dihydrate is neutralized by 23.64 mils of a sodium hydroxide solution, what is the molar concentration of the sodium hydroxide solution? Oxalic acid is a diprotic acid, and what is the balanced equation? Okay, so let's write out our formula. We would have our oxalic acid and it's added with sodium hydroxide. And since this is a neutralization, we would form water plus a salt. So in this case, it would be Na2C2O4. Okay, so now if we balance this equation, you'll see that we have 2 sodiums on our product side and only 1 on our reactant side, so we put a coefficient of 2 in front of sodium hydroxide. And now we have 4 hydrogens on our reactant side and only 2 on our product side. So we're just going to try to fit another 2 in front of the water. Okay, so now everything should be balanced. And let's write down everything that we know for this problem. We know the molar mass of the oxalic acid is 0.147 grams. And we know that its molar mass, oh wait, sorry, this is its mass. And its molar mass is the 126.07 grams per mole. And we know the volume of the sodium hydroxide solution. I'll use a different color. So this is oxalic acid. And for sodium hydroxide, we know the volume that was added to neutralize was 23.64 milliliters, which we can convert to liters as well. 0.02364 liters. And we want to find out the concentration of sodium hydroxide. And its values are in moles per liter. Okay, so this is a multi-step question. And step 1 is to find the number of moles of oxalic acid. So we can do that by dividing the mass by our molar mass. So the mass of oxalic acid was 0.147 grams. Its molar mass was 126.07 grams per mole. And if we divided the two, we get around 1.17 times 10 to the negative 3 moles. Okay, so step 2. Using mole ratios, we can find the number of moles that reacted for sodium hydroxide. Okay, so we know that 1.17, I'll write up here, 1.17 moles of oxalic acid reacted to neutralize the reaction, and we know that oxalic acid and sodium hydroxide react at a 1:2 ratio. So since we're trying to find the number of moles of sodium hydroxide for the mole ratios, sodium hydroxide will be on top. So 2 moles sodium hydroxide, and oxalic acid, which is the moles or the units we're trying to get rid of, will be at the bottom. So if we multiply this by 2, we get around 2.34 times 10 to the negative 3 moles of sodium hydroxide. And finally, we can calculate concentration. So recall that concentration is equal to number of moles over volume. So we know that the number of moles that reacted was 2.34 times 10 to the negative 3. And the volume of solution that was added to neutralize was the 0.02364 liters, which gives us our final answer, which is around 0.098 moles per liter. Okay, so now let's see what the junior tutor said. They wrote out the balanced equation, and they just found the mass of sodium hydroxide instead. This is another way of doing it. And then converted that to moles. So 40. Yeah, so it looks like they just multiplied. I'm not really sure how they did this. But I'm just going to say is incorrect. We need to take into account molar ratios of oxalic acid and sodium hydroxide to solve this question. Okay, so this looks long, but I think it is just a multiple choice. So we just need to draw and describe the Lewis structure for oxygen. And then out of the multiple choice, we need to pick how many bonds are to the oxygen and how many valence electrons or lone pairs it has. And the same for part 2, we need to draw the Lewis structure for carbon disulphide and then pick the option that most pertains to our molecule. Okay, so let's write the Lewis structure for oxygen first. And we first need to calculate the total number of electrons we expect for this structure. So oxygen has 6 valence electrons, and since there are 2 oxygen atoms bonded together, we should have 12 electrons in total. So first let's draw a single bonded oxygen to another oxygen. And if we were to make both of these oxygens have a full octet, then you see we have more electrons than we need. So this particular molecule would have 14 electrons. But if we were to form a double bond, then this would give us our 12 electron count. And if we were to calculate formal charge, so let me write down the equation for formal charge, which is the number of valence electrons minus the number of non-bonding electrons minus the number of bonding electrons divided by 2. And if we did it for one of the oxygen atoms, oxygen has 6 valence electrons. The number of non-bonding electrons is 4. So this is from the lone pairs on the oxygen. And since there's a double bond and there are 2 electrons participating in each bond, then we have a total of 4 bonding electrons that we divide by 2, and both of the oxygens are neutral. So we know that we drew the Lewis structure correctly. So now if we look at our options, option 1, there's a single bond between the oxygen and 6 around each oxygen, so that is incorrect, as we said earlier, since this would be like a peroxide. And there is a double bond between the oxygen atoms and 4 electrons around each oxygen. Okay, so this solution is correct. So it's therefore B. And now we need to draw the Lewis structure for carbon disulphide. That was A. B is carbon disulphide. So again, let's calculate the total number of valence electrons. Carbon has 4, and sulfur has 6. And since there are 2 sulfur atoms, we can multiply this by 2. And if we were to add these values up, we get a total of 16 valence electrons for carbon disulphide. Okay, so let's draw it says to describe all possible Lewis structures for the molecule. So let's just draw the neutral one. So we can have a carbon that is first bonded to the 2 sulfurs. But notice that carbon doesn't have a full octet yet. So then if we were to draw 2 double bonds between the sulfurs and count how many electrons we've drawn so far, then we only have 8 out of the 16 in this structure. So for the remaining 8, we can put them as lone pairs on our sulfur atoms. And we can also show another Lewis structure for this molecule to see what would happen if we were to form a triple bond between one of the sulfurs and the carbon. So if we were to bring these electrons down, then these electrons can move onto this carbon, and we can form a resonance structure that has a triple bonded sulfur to the carbon and then a single bonded sulfur at the end. Okay, so this would make this sulfur have a positive charge and this sulfur have a negative charge. So this is another Lewis structure that we could draw for this molecule. So if we look at the options they give us, either A, there's a single bond between the central carbon and each sulfur with 6 electrons around each sulfur. So we know that this solution is incorrect since carbon needs to have 4 bonds to be stable. And then for B, there's a double bond between the central carbon and both sulfur atoms with 4 electrons around each sulfur, so that's correct. And C, there's a single bond between the central carbon and one sulfur that has 6 electrons, and there's a triple bond between the carbon and the other sulfur with 2 electrons around this sulfur. So that is also correct, which is our second structure. So the answer is part B, choice B and C. Okay, so the junior tutor said to first determine the total number of valence electrons for the molecule O2. And I'm guessing the images didn't really form correctly. But the explanations are all correct. They found that the total number of valence electrons for the second molecule is 16. And they also showed the second structure as well. I just think there's some image loading issues. So I'm going to say this explanation is correct. However, some images may not have loaded properly. Okay, so question number 6 says, given that the molar mass of carbon tetrachloride CCl4 is 153 grams, calculate the mass in grams of one molecule of carbon tetrachloride. Okay, so we know the molar mass is 153, and the unit should be in grams per mole. And we're trying to solve for the mass of one molecule of carbon tetrachloride. So I'll say mass of carbon tetrachloride molecule. So the units that we're looking for would be grams per molecule. Okay, so to answer this question, we also need to write down a helpful number known as Avogadro's number. So this can be referred to as NA. And the reason why we need Avogadro's number is because its units, so it's 6.022 times 10 to the 23, and its units are in molecules per mole. So therefore, step 1 of answering this question is to find the number of moles well, I guess we can fit it all in one step because we can just convert. If we had 153 grams per mole, and if we divided by Avogadro's number, so I'm going to show it as a reciprocal and multiplied, just so that we can see how the units might cancel out. Okay, so then our moles will cancel out, and our molecules are in the denominator now. Well, they've been in the denominator. And this is how we can get the grams of one molecule of carbon tetrachloride. So if we divide 153 by Avogadro's number, you get around 2.54 times 10 to the negative 22. And this is grams per molecule. Okay, so the junior tutor said they just had their data and they did cross multiplication to also get 2.54 times 10 to the negative 22 grams. Okay, so this solution is correct. Okay, so question number 7. Identify the allylic carbons in each of the following structures. Okay, so let's write down the definition of allylic carbon. It is a carbon that is adjacent to a double bond. Okay, so now that we know the definition of allylic carbon, let's try to identify them in our two structures. Okay, so I'm just going to draw this out. And you can see that there are two double bonds in these structures. And I can label which ones are allylic. I'll just label it in red. So it isn't the carbons that are participating in the double bond. They're the carbons that are beside it. So for example, this carbon, not this one since it has the double bond, but the one beside it. And the carbon on this side would be allylic. And the carbons here and here. So these are all of the allylic carbons, and we have 5 in this structure. And now let's do the same thing for part B. And they showed some stereochemistry here as well. And we have just one double bond here. So the carbons that are adjacent to this double bond would be this carbon and this carbon, and also the carbon in the methyl group. So for this molecule, we have 3 allylic carbons. Okay, so let's see what the junior tutor said. Allylic carbons are carbons that are present adjacent to a carbon-carbon double bond. In other words, it is a carbon atom that is bonded to another carbon atom, which in turn is a double bond to another carbon atom in the same molecule. Okay, so they picked the 5 correct allylic carbons in the first structure, and then the 3 in the second structure. So this solution is correct. Okay, so question number 8. Is beryllium dichloride polar or nonpolar? Okay, so let's first write down a Lewis structure for beryllium dichloride. So to write down the Lewis structure, we first need to calculate the total number of valence electrons for this molecule. So beryllium has 2 valence electrons that can participate in the bonding, and chlorine contains 7, and since there are 2 atoms of chlorine, we multiply this by 2. So now if we were to add these values together, we get a total of 16 valence electrons. So now let's draw beryllium as our central atom. And if we were to draw 2 single bonds to the chlorine, would look like this. And we can also show all of the lone pairs on the chlorine as well. So let's just draw them in. And if we count out how many electrons we've drawn so far, where each bond contains 2 bonding electrons, then you can see that we already have our 16 valence electrons in this structure. So to find out whether or not this molecule is polar or nonpolar, step 1 would be to just find the difference in electronegativity So this can be delta En between chlorine and beryllium to see if the bond is polar or nonpolar. Okay, so let's look up the electronegativity values. For these 2 atoms. So the delta En of chlorine and beryllium. So beryllium has an electronegativity of only 1.5 and chlorine's is 3. So the difference between the two would be 1.5. So therefore, the bond is polar since our electronegativity difference is greater than 0.4 but less than 1.69. So since we know that the chlorines are much more electronegative than our beryllium, we can draw dipole moments going towards the directions of the chlorines. But if we look at the Vesper shape of this molecule, so let's also look up Vesper table. And if we were to analyze our Lewis structure, we can see that our central beryllium atom has 0 lone pairs and 2 bonded atoms. So its molecular shape is linear. And already we can see in the picture that the two dipole moments in chlorine will cancel each other out, since there are no lone pairs on the beryllium to offset the dipole moments. So since we have a linear structure, this means that the dipole moments do cancel each other out. So therefore we have a nonpolar molecule. So this is an example of even though we have a polar bonds involved in the molecule, we can still have a nonpolar molecule if the dipole moments cancel each other out. So we can call this as a zero net dipole moment. Which makes it nonpolar. Okay, so let's see what the junior tutor said. So it looks like they fully explained what a polar molecule is when two atoms do not share electrons equally in a polar covalent bond, and when there's a slight positive and slightly negative charge on each of the atoms. And they also have some polar molecules as an example as well. So water, ammonia, hydrogen sulfide, and ethanol. So a polar covalent bond exists with atoms with different electronegativities, for example, HCl. And they have the definition of nonpolar molecules. When atoms sharing a polar bond arrange such that the electric charges cancel out. Okay, so yep, so when you have polar bonds and they cancel each other out, you can have a nonpolar molecule. And they also have, if there's a nonpolar covalent bond, electrons are evenly distributed. Okay, so when the electronegativity difference between two atoms is less than 0.5, it's considered nonpolar. Okay. And they say even though the only truly nonpolar molecules are those formed with identical atoms, so like diatomic gases and the noble gases as well. And they said that this is a nonpolar molecule since it is symmetrical. The dipole-dipole moments are cancelled out, and it has a linear shape. Okay, so this solution is correct. Okay, so those are all the questions for this session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, you can give it a like and a comment, or share with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.